Hello students, welcome back. Let's discuss some advanced aspects of problem 2. A fair warning, this is not for everybody. I'm preparing this video particularly for the students who are preparing for Math Teacher Certification exam because this very issue showed up multiple times both in high school teacher certification exam and middle school math teacher certification exam. I advised many of them and I encountered this very issue multiple times there. I have never advised elementary school students preparing for math portion, so I cannot say for certain. Otherwise, this probably is not for you. Oh, maybe there are some IT students who are into data science. In that case, you can stick around. Okay, here we go. 2.1 and 2.2. At first glance, they look identical because 170 out of 250 is nothing more than 68%. So at first glance, it looks like 2.1 and 2.2 are identical problems, just written in different fashion. And I treated it like that in my original lesson videos. And then the answers were the same, and so on and so forth. But in fact, they are different. This one here, down here, 68% is given in terms of proportion. So it stays as proportion. So this problem is for solution, which we discussed for 2.2, stays the same. But this one here, the previous problem we discussed, or the previous solution we had in the previous video, is actually a little bit wrong. And I said a little bit wrong, so with that much error, I'm going to take it as full credit in my class. But if you take some other exams, especially state standard exam, Texas exam especially, then it's going to be counted wrong. What's the difference between the one and the other? Let's take this aspect here. Okay, let's consider these two versions. So 2.1, again. Okay, let's label them as A and B respectively. Same as before, more than 170. And then here, more than or equal to 171. What's the difference between one and the other? Actually, there is none. Can you consider 170.5 person or 170 3/4 of a person? You can't. In short, number of people is a discrete random variable and it takes only integer values, positive integer values between 0 and 250. The normal approximation, on the other hand, is a continuous random variable, so it takes arbitrary real values between 0 and 250, and as a matter of fact, even beyond, from negative infinity to positive infinity. They differ, of course, but the difference is relatively small. That's why it is called approximation. But in this regard, the approximation fails. Well, okay, all right, it doesn't downright fail. We can make it right, but here, more than 170 versus more than or equal to 171 are supposed to be equal. The same because, because of what I just discussed here. So x is greater than 170 is equal to probability of x is greater than or equal to 171. These two have to be the same. However, if I take z-score as 170 minus center 155 over, let's see, what is the standard deviation? I already forgot. So let me go back there. And yes, here's a computation, square root of n p1 minus p. And let's take it downstairs here. And then everything is approximation in statistics. So let me change this into Wrigley equality notation. And let's calculate that. And yeah, I remember that figure. And then that means x is greater than 170 can be approximated by z-score is greater than 1.95, something like that. And that can be calculated, let's see, and then, okay, oops. Okay, that's it. And 1 minus of that and there you go. That's what we got before in 2.1 in the answer queue over there. Draw a picture. And then z-score and z-table, yeah, that's what we got. If you use z-table, then you have to cut only 1.95. So your probability value is not as accurate as this. So you're gonna get 0.0256 or something like that. This one is a little bit better. Now, what if you take this 171 and do the same thing? So this is supposed to be 171. So if I calculate this one, and instead of 1.95 something, you're going to get that. And then you can rewrite like this. That's greater than or equal to 171. And that's greater than or equal to that. And then okay. Normal distribution. And then this quantity. So that's what we get, a little bit different. And then if I calculate this entire thing, what do you get? All right. I got the computation done, and don't pay too much attention to all these mathematical commands. I'm going to erase all those. My point is, by taking z-scores with n minus center over SD with two different values, 170 and 171, we get two different normal approximations, and they differ quite a bit. And we have a problem because these two probabilities must be the same. That's because the original random variable x is discrete. It takes only integer number of people. So greater than 170 and greater than or equal to 171 should be the same. But if you take continuous random variable, but then they're different, and then that's why we have this kind of error. Now, how do we make it right? And which one of them is correct? Actually, neither is correct. The best way to mend it, 170 and 171 are equally as valid or equally as invalid. So let's mend it using the z-score computation as 170.5. then the z-score computation, n minus center over st, is going to become a little bit different, somewhere in between these two, of course, because I took 170.5. So this one and that one are adjusted into that. And then, why did I erase that command? And, oh, I need one more here. Okay, and then that is 0.97 something. And then 1 minus of that. There you go. And I claim the last one is the best. And you see, using 170, we get this approximation. Using 171, we get this expression, but they have to be the same. And they're equally as valid and equally as wrong. So why don't we settle in between as 170.5? And we get this alternative z-score computation. And then if you look up the z-table, let's see, we have plenty of time, so let's do it with z-table as well. So this is approximately equal to 2.02. And then let's look up 2.02. And then let's look up the z-table. 2.02. 0.9783. So if I subtract, yeah, looks like this is what I'm going to get. And even if you use z-table, you get actually very, very good approximation. And this one, of course, is a little bit better. I use computer algebra system. This one, I took 2 decimal digits and looked up z-table. But compared with these two given by computer algebra system, I got better results even with z-table. So this 0.5 technique is actually turning out to be a very, very successful trick. And how do I know these are actually better approximation? It is possible to use brute force computation nowadays. Let me copy and paste that. And this is real probability using some brute force computation with 250 people with all those probabilities with binomials in there. And that's supposed to be 2.0207 something. And as you can see, the green values are much better than red or blue. And this kind of computation was not possible in 1960s, 70s. Even in 80s, you needed some expensive computer. Expensive, I mean by something you cannot own as an individual, something like $10,000 or higher. In those computers could handle. And in 1990s, now personal computers could handle these kind of calculations, but still it took several minutes. And of course, nowadays, you just witness it. It took less than 1/10 of a second, maybe a 100th of a second. So we can easily check. But at the time, we couldn't really check. And all we could do is approximation. And historically, normal approximation turned out to be a really useful tool. And we had been using it for centuries, actually. Nowadays, relatively less important, but theoretically still valid. Okay, that's where I'm going to stop. And please remember this 0.5 trick, especially if you're preparing for text test exam or any kind of standardized exam.